Okay, so let's get started. Lecture 4. Today we will talk about the physical layer. So let's get started. A short review. We talked about internets. Internet's a network of networks. And then we talked about two different models for protocols, the OSI model and the internet model. Important things is there are a number of layers, they have numbers, and they have names. And if you ask me whether you need to know this by heart, I think this is one of the things that would be useful to actually learn, to have, so you know the names of them. And then you fill this up with what the functionality of the different layers are. So this is actually worthwhile. Hammering into your head as you do with your multiplication tables or whatever, so you know which layer is on top of what and what they do. TCP/IP protocol suite is the practical one, the one that we would use as a running example throughout the course, acknowledging, of course, that there are other types of networks out there, but these are the, by far the most common ones. So there's here we only depict 4 layers, but the lower 2 layers here are merged into one. It's a number of protocols that reside in each layer. And so what we talked about last time, we talked about IP, and then we talked about these 3 protocols in the transport layer. And then previously we have talked about a few of these application layer protocols also. So IP here is sort of the workhorse, and what it does, it transmits packets using best effort. Best effort is just another name for unreliable. Okay, so it does its best, but it doesn't guarantee anything. It's a connectionless service, and it transfers packets. Connectionless means that it doesn't establish a connection with the receiver before sending data. It just pushes data into the network. And then the 3 services that run on top of these, UDP, TCP, and SCP, refines the service of IP in different ways. UDP essentially does nothing. So UDP just copies the service we get from IP. TCP provides reliability. And it's also a connection-oriented protocol. It provides full duplex, and it provides a stream service, meaning that we can read and write bytes through these TCP connections. SCP actually refines even further from TCP, providing reliable and connection-oriented is the same. Multi-homing here means basically that it can use several IP addresses as transmitting IPs and receiving IPs at the same time. Full duplex is the same as TCP. Multi-stream is that it can handle multiple streams at the same time. While a TCP connection is a single stream, SCP can use multiple streams. Okay, and then we talked about address concepts, and in TCP/IP there are 3 important ones. There are more than these, but 3 important ones that we talked about was internet names, network addresses, and link layer addresses. So internet names are for human consumption. So it's specifies some type of service. Typically we know that this is a web server. IP address is needed for the IP layer to transmit data between different IP protocol entities. And link layer addresses are for instance, Ethernet MAC addresses. But there is typically a link layer addressing scheme for each type of technology that you have. Ethernet, Wi-Fi, LTE, whatever, right? So many different things here. So internet names are for humans. IP addresses is to transmit packets over an internet. IP addresses identifies a network interface card. Link layer addresses are used to transmit frames between nodes on a network, a single networks. It also identifies a network interface card. So both of these are actually needed because they serve different purposes, even though they point to one network interface card, both of them. DNS is used to resolve, that is, translate between internet names and addresses. ARP is used to find link layer addresses. for the network interface card with a certain IP address. So if we know the IP address, we can use ARP to figure out the link layer address of that network interface card. And then we went back and talked a little bit about the OSI reference model. These 7 layers, the top four layers here, the application down to transport, are end-to-end protocols, which means that if we have a protocol that runs in the application layer, it talks to the application layer protocol at the other side of the network. In contrast to the network layer, which talks to the many of the different network, basically all the network entities which are inside the network. So the network layer at one end does not directly talk to the network layer at the other end. There are some intermediate nodes in between. Okay, and data link is the same, and physical layer is the same. So the topic of today is to dive into the physical layer. We'll talk about that for a couple of lectures. And then as the course progresses, we're going up to the network layer and talk about this and maybe touch a little bit. We go up to the data link layer and we'll talk about that and then maybe touch a little bit on the network layer again. Okay. So if one is interested in more details in the upper layers here, there are other courses to take, obviously, right? So there is just so much we can cover in a class like this. Okay, so if we then go back and say, okay, physical layer here, there is a whole community, a large community that deals with physical layer communications, and they of course have models on how communication happens. And this is a quite famous model called the Shannon's communication model, and it's named after a person, Claude Shannon, who seemed to be the father of a field called information theory. Okay, it doesn't fit very cleanly into the model we had earlier about the physical layer, and I will tell you a little bit about the differences. But it's an important model in itself to be aware of. What we have here is we have a source that would like to communicate data to a sink. So the source is the generator of bits. All the black lines here are bit streams. Okay, so there is a bunch of bits coming out of this source with a certain rate, certain number of bits per second, and then it goes to the source encoder. So the source encoder is data compression. Okay. So what do I mean by data compression? That basically means that there is a number of bits coming in here, but there are fewer bits coming out of here, although this can be done without loss of information. Okay, so if you probably use this, but if you have a file, a text file of say 100 kilobytes, you can compress it down to maybe 20 kilobytes without lose and decompress it again, and then you retrieve the original text. So there is a lot of redundancy in text that could be compressed down to the bare essential information, and this is of course useful if you want to cram in a lot of information on a limited storage device. But it also serves a purpose here in communications, because if we have here say 1 megabit per second, and the same information we can get with 100 kilobits per second, both of these streams carry the same information, then it's more economical to transmit the information part rather than the information plus some redundant stuff, right? So here we do data compression in the source encoder. Now, going to the next step, the channel encoder, what it does, it's for data protection or error control. And this is done by adding bits, okay, control bits, or parity bits, or check bits. Okay, so actually the data rate after the channel encoder is higher than the input, okay, because we add bits. So maybe this is 120 kilobits per second. Okay. So it seems maybe a little bit odd that we first do data compression and then we remove bits and then we add bits here. The difference here is that we add these bits in a very controlled way so that later we can detect and possibly correct errors. So this is not a, what shall we say, it's not so contradictory as one might think. Okay, so we have a bit stream here and we have a bit stream here. And now it's time to transmit these bits over a physical channel. Now a physical channel cannot handle a bit stream. It has to handle some type of waveform which is suitable for this channel. So maybe it's a radio wave or maybe it's an electrical current or whatever it is. But at least it's something which is in red here, which is an analog waveform. So the modulator, the task of the modulator is to take bits and produce waveforms. So in its bare essential, this is digital to analog conversion, the modulator. A very particular type of digital to analog conversion, but still, that's what it is. Okay, so this is then the signal that leaves the transmitter, and then it goes over the channel, and the channel distorts the transmitted signal in some way. The typical thing is that it adds some noise to this, some unknown, unpredictable waveform. And then we have the received signal, and the transmitter consists of 3 blocks again that essentially undoes or do the reverse of the transmitter blocks. So the first block here, the demodulator, is basically an analog to digital conversion. Okay, and then we have here some bits, and these bits, the bits here ideally should be equal to the bits up here, but there are some errors typically introduced during transmission over the channel. And the errors is due to the distortion that the channel introduces here. So there are typically some errors here, and the purpose of the channel decoder is to find these errors and correct them. Okay, so okay, and then we have some bits here. Okay, and ideally they should be equal to these bits. Now typically there are sometimes this error detection is not perfect, so there might be still errors in this. Okay, for our purpose, okay, and these errors is if they're few enough, then the source decoder will still produce a bit stream here which is good enough. Okay, so say that we send over a video. Okay, then perhaps not every single bit in the video here is sacred, in the sense that maybe 1 bit out of 10 billion bits was corrupted, and that is not noticeable when you watch the video. Okay, so there's still maybe some cases where you can tolerate errors here or distortion, that is, you can tolerate errors here. Now in our course we typically don't tolerate errors at all. Okay, so we want this to be error-free. So I would say that we would like really this to be no errors here. And we will see later on how we can essentially achieve error-free transmission over a noisy channel. Okay, so it might seem counterintuitive now, but we can, over a channel which is noisy, have error-free transmission. And when I mean error-free, I mean virtually error-free. You tell me what error probability you would like to achieve, and we can design a system for this. So if it's 10 to the minus 200, that probability, which is super tiny, right, we can achieve that. And we can say that that is essentially 0. Okay. Now, so this, to couple this model, the Shannon communication model, to the model we had before, the ISO model, the source encoding and decoding, these are typically put in the application layer. So it's not part of the physical layer. Okay? While the channel encoding and modulation is typically thought of as part of the physical layer. Sometimes the error control is placed in the data link layer, and then the physical layer is basically just a modulator, demodulator. Okay. So it's not a perfect match between these models, but you know, that's what it is, right? It's not a perfect world in this sense. Okay, any questions before we continue? Okay, so the name of the game now is to transmit bits. Okay, so that's what we will be concerned about. And going back to the this Shannon model, so we will talk now about the modulator and demodulator, and then we will add on noise to this and to see what problems that causes. And then we will continue to try to figure out what is the probability of error over these type of channels. So that's a sort of a high level what we will do now for a couple of lectures. Okay, so we start with transmission over noisy channels. So again, we have some noise here. So that's the noisy channel. We have some bits to start with. Okay, so here we have capital K bits. 1, 4, 6 bits, whatever, or 1,000 bits, I don't know, a number of bits. These bits needs to be translated into a transmitted signal. So that is the purpose of the modulator, right? To take some bits and produce a signal, digital to analog conversion. Okay. So an example of this is that we take a block of bits and then we output the signal. So an example modulator should map each possible k-bit input pattern to signal alternative, to a type of signal, right? So what do I mean by that? Well, suppose that the input is the all zero pattern. Okay? That should be represented by some signal. Let's call it S1. Now, the second pattern is the all zero pattern except the last bit, which is a 1. Then that should be represented by a signal. I think it's pretty clear that it would be bad if it was the same signal, because then how can the receiver distinguish between these two transmitted bit patterns? So S2 here needs to be something which is different than S1 for this to make sense. So essentially, we assign a unique signal to each possible input pattern. Okay, so that is the modulator. So conceptually, it's a super simple device. It basically takes a bunch of bits and then outputs the corresponding signal. So there is no very difficult processing going on here. Okay, any questions on that? Okay, so how many signal alternatives do we need? Well, we have k bits. So 2 to the power of k is the number of possible input patterns. Or for each of those input patterns, we need an output signal. So the number of output signals, m, is 2 to the power of k. Okay, so 4 bits in, 16 signals. 2 bits in, 4 signals. 1 bit in, 2 signals. Right. Okay, so the next step is then in the chain here is the received signal. And the received signal in the simplest case, when the channel does nothing but add noise, is that the received signal is the transmitted signal plus some noise. And it's the task of the demodulator to look at the input signal and then guess a bit pattern that hopefully is the same bit pattern as what was input to the modulator here. Okay. So the demodulator maps every possible input signal to a decision, or a guess if you like, on the transmitted bit pattern. So it observes the received signal and it spits out k bits. Okay. And the objective is, of course, we would like this ideally to be equal to the transmitted bits. Okay. Questions? Okay. So a concrete example of this is that if we have two bits, B1 and B2, and then look at what the output signal should be. If we have 0, 0, that should be mapped on, say, onto a signal, and let's say it's like this signal. Okay, so this is S1 of t, and maybe this, we call this t over 2, like this. And then we have 0, 1 is the next pattern, and that's mapped onto another signal. Maybe it looks something like this. This is called S2, which is a square wave of duration t seconds. We have 1, 0, and that should be mapped onto some other signal. Let's call that S3. And I'm running out of space here, but let's try anyways. 1, 1 should be mapped onto something. And let's go with a full negative signal like this. And this is S4 of t. Okay. So this could be one example of a modulator. Okay. So 2 bits in, 4 possibilities, 4 signal alternatives. Okay. So, yeah, well, okay. Lecture quiz then. So if we want to transmit 4 bits, how many signal alternatives do we need? 4, 8, or 16? Give you 10 seconds to think about that. So how many for 4? How many for 8? And how many for 16? That was too simple, right? Okay. So next thing is maybe a little bit more harder. So what does the demodulator need to decode the transmitted bits? Okay, so for alternative A, it needs the bit to signal mapping and the observation of the received signal. B, it needs the signal alternatives and the observation of the signal. C, it needs everything, so bit to signal mapping, signal alternative, observation of the received signal. Or D, bit to signal mapping and the signal alternatives. I'll give you 10 seconds to think about that. Okay. So how many for A? B? C? And D? Okay. Correct answer is this one. Okay. And the reason is that the receiver needs to know what type of signals are transmitted. So the receiver needs to know these, right? Otherwise, it would be hard for it to distinguish between them. And to figure out the bits, it also needs to know the mapping, the assignment of bits to signal, right? But this is no big thing, right? This is something which is decided at design stage. It's put into the software of the receiver, so that's no big deal, right? What varies from time to time is the observation of the received signal, because that depends on the noise and also depends on the actual signal that was transmitted. But the mapping between bits and signals is well known. It should be established. Okay, we continue. So, how do we figure out the best receiver here? Okay, so suppose we're the receiver now. Okay, so this is what we know. Okay, so this is something which is part of the design. So this is known to us. And now comes the observation here. Okay, so this is the received signal. Okay, so our task now is to look at the received signal and figure out and decide what bits we think were transmitted. So what would you think in this case? Let's make it a little bit easier, actually. If the received signal was something like this, what would you guess the transmitted bits were? 0, 1. And why is that? Yeah, so the blue one here looks more similar to S2 than to any others, right? Okay, so yeah, so it's probably this one. Now, the white one, what would you think then? It's harder, right? Okay, so it's not super clear to me, but maybe one can still think that it's S2. But if the received signal is something like this, it's really hard to do this, right? Okay. Now, of course, we as humans can somehow see similarities between signals, but how do we make a machine, the demodulator, to do this, right? Okay, so the idea here is that we use, there are several ideas on how to do this, obviously. There are many choices we could do, but I will present one which is a very good choice, and that's called the minimum distance receiver. So let's work this out. It's four simple steps, conceptually simple steps. So the first step is that given the bit to symbol mapping, okay, we know that. The signal alternatives, okay, we know that. And the received signal. So basically, we know everything here on the blackboard. So this is the input to the algorithm, okay? Number two, what we do is we compute distances between the received signal, R, and all possible signal alternatives. SL for L equals 1, 2, 3, up to capital M. Okay, so what is the distance between two signals? Right? We know what the distance between 2 points is, but what is the distance between, say, this white line and this white line, or these two functions? What is the distance? Okay, then that is defined as follows. It is defined, the distance between R and SL is defined as we take the difference between R and S, magnitude squared, this is a function, and then we integrate that and we take the square root of it. That's the distance. Okay. Now, if R is equal to SL, this becomes 0. If R is not equal to SL, this becomes non-zero, but positive. Okay. So it's a positive thing, which is distance is, and it's 0 when the two objects that we measure distances from is equal. Okay, and then it fulfill other requirements also, which we typically have with the distance metric, triangle inequality and things like that. We won't go into the details here, but you could just believe me that this is a good metric that fulfills intuitively what we mean by distance. Okay, so once we have calculated this, and we want to calculate this for L equals 1, 2, up to capital M, so for all signal alternatives. And once we've done that, we choose the signal alternatives with the smallest distance. Okay, we select the signal alternative out of these 4, which is closest to what we have observed. This is what we did, what you guys and girls did by just looking at this. Right? Now we have a machine to do this for us. So these distances that we calculated here, dl, we plot them as a function of L. And then we look at the values of this, and we take the smallest one, and our guess is the index of the smallest one. Okay. So in mathematics, the signal alternative index, M hat here stands for guess, by the way. So hat equal guess or estimate. It has nothing to do with Fourier transforms or anything like this. It's just a notation which is used in the field to denote estimate. Okay, so M hat is the index to the smallest distance. So in mathematics, we write this as arg min of distance. The minimum distance is the amplitude here, while the index is the arg of min. So arg min means the L, which corresponds to the smallest distance. Maybe I said this in an overcomplicated manner. Do you think this is difficult? Unclear? No? Okay. Basically, we would like to find the closest distance and the index to that. And then the final step is to look at our guess of the signal that was transmitted. So M hat here defines a signal, and then we demap that to a corresponding bit pattern. So basically, if we think that S2 is closest to this, then our decision is 0, 1. Okay. If we think S3 is the closest one, then our decision on the bits is 1, 0. So we undo the mapping, called demapping. So questions on this? It was clear? Pretty clear, I hope? Okay. So yeah, so this is it. This is what the demodulator does. So in principle, it's not a very difficult device. It just needs to take the input signal, subtract off the known signal alternatives, and calculate these distances. And you need to do that for all the signal alternatives, and then figure out, okay, which one is the best of those. And once we've done that, to figure out, okay, what are the bits that corresponds to this signal alternative. That's it. Okay. Questions before we continue? No? Okay. So let's see how we do this in a more practical way, because the mapping here is not okay. It can be done in many different ways. In this course, we will only talk about one and the possible twist of this generic structure, which is called a pulse amplitude modulator. So this is heavily used in practice in different variations. So it's worthwhile to learn about that. So pulse amplitude modulation. It's a modulator, so the input is bits and the output is a signal. Okay? Digital to analog conversion. So it's done in 2 steps. The first step is to take bits and then map them onto a amplitude. Okay. So the first step, the mapper here maps bits into symbols or amplitudes. An example of how this could be done is as follows. So say that we have the all 0 input, then that is mapped to amplitude A1. The all 0 but the 1 here is mapped to A2, and the all 1 pattern is mapped to some amplitude A capital M. And these amplitudes is something that we design. It could be different amplitudes, but they are distinct. They're different amplitudes. And we will see later on what a good choice of amplitudes are. But for the purpose now, they're just some amplitudes. And we put these amplitudes into a set that we call the symbol alphabet. Okay. So what the mapper does is to take a block of bits and then output an amplitude. And the amplitude is chosen from this set of amplitudes. Okay. Questions on that? No. Okay. So the bits are encoded into an amplitude, a real valued number, typically. Okay. And then this number, this symbol or amplitude, is then transmitted over the signal in the following form. We take the kth amplitude. Okay, so k here is some type of time index, just as I is a time index. So, but if we take a block of bits and then produce out an amplitude here, this is further mapped to a pulse. So, in the pulse amplitude modulator block. So, the pulse amplitude modulator block is defined by a basic pulse shape that we choose, maybe a rectangular pulse or something else. And then every t seconds, it takes an input, an amplitude, and then spits out that amplitude multiplied with the basic pulse shape. Okay. And then it repeats itself for all time indexes k. Okay, so for the first symbol, it outputs the pulse times the amplitude. For the second input, it outputs the same thing, just translated in time. Okay, so a simple example of this is that, say that we have a symbol alphabet consisting of -3, -1, 1, and 3, 4 real valued numbers. And then what we need to do is to map bits onto amplitudes. So if we're interested in the kth, k is a time index now, so the kth symbol, then that depends on 2 input bits. Okay, so just to make the time index for the bits and the symbols to align, we can write this as the first bit is the 2k minus first bit, while the second bit is to the 2kth bit. Okay, it's not super important that you keep the indices in your head right now, but this, trust me, this will work out. Okay. So adjacent blocks of bits are mapped onto amplitudes or symbols, that is amplitudes. So 0, 0 may be mapped onto -3, for instance. 0, 1 be mapped to -1, 1, 0 to 1, and then 1, 1, 2, 3, say. Okay. So now we have defined the mapper. Okay. This defines the mapper. And then we also need to define the pulse amplitude modulator block. So we need a basic pulse shape. And to make it simple for drawing, we just pick a square wave here, maybe has some duration t0, and say that it has amplitude 1, just to make things simple. Okay. So, and now we only need one more thing, and that is the number capital T, this capital T here, which tells us how often we transmit pulses. And just to define that in relationship to T0, let's put that here, T. Okay. So now everything is defined. Okay. So then let's see how a sequence of bits goes through this mapper to become amplitudes. So 0, 1, 1, 0, 1, 1, for instance. So we have a stream of bits coming into the to the mapper. So we need to define, okay, is this the first bit or is this the first bit? I'll say that this is the first bit. Okay. So first, second, third, fourth, and so forth. And we block them in blocks of 2 bits, because we have 2 bits in for each amplitude that we put out. Okay. So 0, 1, 0, 1 becomes -1, so that's our first amplitude. 1, 0, 1, 0 becomes 1, that's our second amplitude. And then the third input is 1, 1, so that will be output amplitude 3. Okay. So here's the action of the mapper. So you take blocks of bits and represent each block of bits as an amplitude. And then a stream of input bits becomes a stream of output amplitudes. Okay? All right. So what is then the signal here that we get? S of t. Well, we have 3 amplitudes here. 1, 2, 3 amplitudes. Each of them is represented by a pulse. So the first amplitude is -1. So we take -1, we multiply that with the pulse shape. Okay. This is g of t. And that's our first part of the transmitted signal. So it will have amplitude -1. It will go like this, and it will terminate at time t0. Okay. So that's the first amplitude that we send, the first symbol. Okay, and then t seconds later, or at time t, capital T, it's time to transmit the second pulse. And the second pulse should have the amplitude 1. So then it's this pulse. Right. So this is okay. So this is A0, A1, and A2. So this is A1 times G of T minus capital T. And then at time 2t, we need to transmit A2. Okay, and it's amplitude 3, multiply that with G, and then we get, okay, the scale is not super good here, but suppose that this is amplitude 3. Okay, and here we have A2 G T minus 2 capital T, like this. Okay. So hopefully the principle is clear now. For each block of 2 input bits, we produce 1 output amplitude. That output amplitude is multiplied with a pulse and then delayed by an integer number of capital T seconds. So we get a train of pulses here. Questions? So this is clear? Okay. So how about if we, so we'll do one thing and then we have a break. Okay. So and this is something that I know from experience that people sometimes have a problem to get this straight in their heads. So let's pay attention to this. Now, we transmit pulses every capital T seconds, right? So what is the rate? How many pulses per second do we transmit? Well, we transmit this rate. So the symbol rate, or pulse rate, if you like, is 1 divided by capital T. So these are the number of symbols per second. Symbols per second. Okay. How many bits per second do we transmit? Well, that depends on how many bits we transmit per symbol, right? We know the symbol rate. It's 1 over T. How many bits do we transmit per symbol? Well, that depends on how many signal alternatives we have. All right. In fact, what we have here, if we have k bits in, then we need m equals 2 to the power of 2k signal alternatives. So another way to write this is that k is the log. Oops, this becomes too small. K is equal to the 2 log of m, right? If m is 2 to the power of k, then k is the 2 log of m. Okay, so therefore, the bit rate, the number of bits per second we transmit, is the log 2 of m divided by t. Okay, so this is in bit per second. So which one is highest, the bit rate or the symbol rate? There's no break until somebody answers. The bit rate, right? And why is that? It's because we carry more than 1 bit per symbol. That's the smallest we can do, is 1 bit, 1 symbol, right? But we can have multiple bits in per symbol. So if we transmit, say, 2 bits per symbol, then the bit rate is twice the symbol rate. If we transmit 3 bits per symbol, then the bit rate is 3 times the symbol rate, and so forth. Okay. So now we can take a break.